All right. Welcome back again, everybody. Today we're going to be doing section 6.8. This is the trigonometric identities section. There is a lot of stuff to talk about here, so this might run a little bit long, and I do apologize, but I will assuage some of your worries as we go along, so don't worry too much, all right? Okay, let me get the slides pulled up and let us get started. Hang on a second here. There we go. Oop, one more thing. One more. Okay, there we go. All right. So first thing I want to do is go through the overview. And I'm going to begin with a little bit of an introduction and a little bit of a disclaimer about this section and about, well, just how many trigonometric identities there really are. Then we're going to talk about the definition of an identity. We're going to talk about how to prove an identity. We're going to do a lot of proofs in this section. This is the section where you have to basically prove a whole bunch of identities. We're going to talk about the Pythagorean identity and alternate Pythagorean identities, the even-odd identities, the angle difference identity for cosine. We are going to prove that one. And what's interesting is that we're going to use like an algebra geometric argument for that. And what we're going to find is that once we have that one identity, all the other identities we're going to discuss fall out from just algebraic tweaks of that one identity and the other ones that we prove along the way. It's kind of interesting. So then we'll talk about the angle sum and difference formulas for sine and cosine, the double angle identities for sine and cosine, the power reducing identities for sine and cosine. And then at the very end, I've got a slide of trigonometric identities that you do have to memorize. And hopefully I can motivate your memorization of those identities when I get there, but I'll start by saying this. I tell all of my classes and at this level, like pre-calculus, calc 1, calc 2, calc 3, you got to have these ones memorized at least, right? Okay. So, a little bit of an introduction and a disclaimer. We're going to derive and prove several trigonometric identities, a lot of them. Most of these trig identities follow from clever algebraic manipulations of identities that we already know or have already proven earlier, like in this section. So because of that, there are literally hundreds of them, hundreds of trigonometric identities. Trigonometry is one of those subjects of math that just lends itself to a lot of really clever and even elegant equivalent manipulations of things. You'll see in today's lesson. If you're interested, you can check out the Wikipedia page that has a list of trigonometric identities, and you will see just how many of them there are. There's just hundreds of them. So trig identities are useful because they provide a way of expressing more complex trigonometric expressions in terms of simpler trigonometric expressions. And that can make our work a little bit easier. In particular, in Calculus 2, and Calculus 1, you're going to use these identities to make things easier. That's why they're important, okay? Now, here is the disclaimer. We will not be deriving all of them. We're only going to derive some that are particularly relevant to the calculus sequence, okay? So if you haven't taken trigonometry before, or if you've seen this before, or if you go to the math lab or the tutoring center and you see students fretting about this, this is classically when a lot of trig students fret about needing to memorize so many formulas because there are hundreds of them, and many instructors require you to memorize dozens and dozens of them. So here, instead, I'm going to do what I've done in the past, which is I'm going to distinguish a small handful of formulas that you really do need to memorize, and then a handful of others that you should recognize. All right, the difference between memorizing and recognizing a formula or an identity, okay? Now, that being said, just because I'm saying you don't need to memorize all of these, if you're interested in doing competition mathematics, for example, like the AMATIC competition or like the Putnam exam or things like that, then you should memorize as many identities as you possibly can. So that's one of my disclaimers there. The other thing is some instructors may require you to memorize more of these identities as you go further along. All right, so just be aware that that may be a requirement later. Another note to say about these things. Honestly, you're going to have a lot of time and opportunities to memorize some of these other identities in your major courses when the application becomes relevant, where it's like, oh, I may not require you to memorize this identity now in this course, but when you get to another course, one of your major courses, your instructor may require you to memorize it then. Well, you've got time and you can see the relevance of it there. Whereas now it's just some arbitrary identity. So that's my disclaimer. All right. Okay. Uh, oh yeah. I said this before. So as with the standard angles, when it comes to trig identities, there's a difference between memorizing and recognizing. So when I say memorizing a formula, I mean you should be able to recall quickly and exactly what that formula is from memory without any assistance. You should be able to pull it out of your back pocket instantly, ready to use at any time. Okay. Recognizing a formula means when you see a structure, you should kind of be like, that looks familiar, and I'm pretty sure there is a formula related to that structure. And I think it's one of these formulas, and then you can go look it up. That's the difference. So, recognizing a structure and being able to use an external resource to find out exactly what the identity is, that is recognizing a formula. Memorizing means pull that out immediately out of your back pocket, as in if you're walking down the street and somebody says, hey, give me the double angle identity for sine, you should be able to answer it instantly without having to like look it up or anything. Okay. All right. So what is an identity? So here's the definition. We say that two functions f and g are identically equal if and only if f of x equals g of x for every value of x for which both functions are defined. The every value of x is the important part here. We're saying that this equation is true no matter what x is, okay? Now, if this condition is satisfied, then this equation is what we call an identity. With identities, sometimes you will see this notation. It's like a triple bar. That triple bar means identically equal. Sometimes you'll even just see that the functions themselves, like the rules, are identically equal. So if you see that triple bar, that's what it means. I think I actually used it once back in section 3.8 or 3.9. But sometimes that'll get used just to emphasize that these things are identically equal, not just conditionally equal, which is what we call a conditional equation. So an equation that is not an identity is referred to as a conditional equation, which means it holds, but under some conditions on the input. If it's an identity, it doesn't matter what the input is. It's true for every value. There's no condition on that. But if the equation only holds for some x values, it's a conditional equation. So here are some examples right here. These three things are identities. So x plus 1 squared is identically equal to x squared plus 2x plus 1. It doesn't matter what x is, this equation holds true for every single value of x. Here's another one. This is that Pythagorean identity, which we're going to talk about in a moment here. You've already seen this one. Cosine squared x plus sine squared x equals 1. That is true for any real number x. It doesn't matter. That's true. Here, cosecant of x is 1 over sine of x. That is true for any value of x as long as sine of x is not 0, right? So those are identities, identically equal expressions, these things, all right? Now, down here, I've got a list of conditional equations. So, for example, this equation, it's not true for every x, right? It's only true, in this case, it's only true for one x value. It's true when x equals negative 5 halves, right? So, this is a conditional equation, the condition being x has to be negative 5 halves, and then this is true. Same thing with sine of x. Sorry, sine of x equals 0. That's a conditional equation. It's not true for every value of x, right? It is true for infinitely many values of x. As long, these are just the zeros of the sine function, but it's not true for every x. So that's the power of that word for every, right? Keep that in mind when you get to Calc 1 and Calc 2 and Calc 3 also. That for every changes the game quite a lot because here there's infinitely many solutions to that equation, but that doesn't mean that every x is a solution to that equation. Same with this one. Sine of x equals cosine of x. That's a conditional equation. Sometimes these values will be equal. Maybe you can kind of imagine when they would be equal. When is sine of x equal to cosine of x? I'll let you ponder that on your own. Okay, right. So a lot of what we're going to do today is prove identities, and there's some rules for how you're going to do this. All right. So how to prove an identity? Well, if we want to establish or prove an identity, it means we need to use algebraic manipulations and previously known identities to show that another identity holds. That's the goal. So to do so, here's how we do it. We start with one side of the proposed identity and arrive at the other side through valid manipulations. Okay. So I'm going to emphasize this a couple of times, but you've got to start on one side and arrive at the other side. That's the simplest way to say it. Okay. So here is a cautionary note. If you try to start by writing down the proposed identity and then working on both sides, that is not a valid approach. Okay, so you can't, if I ask you to prove an identity and you say, okay, here's the identity, and then you start working on both sides and then you get something obvious at the end, like 1 = 1, that is not a valid proof of the identity. Okay, you got to start on one side and then derive the other side. That's what you have to do. There's like another way to do it where you can start on one side and get to like a middle, and then start on the other side and get to a middle. But that turns out to be equivalent to starting on one side and getting to the other side. So, moral of the story here is don't start by writing the equation down that you're trying to prove. That's not going to work. Start by writing one of the sides down and then massage things, get the kinks out of it, and then you'll have the new result, and that'll be on the other side. Okay. Um, yes, yes, yeah. So there you go. Start on one side and write your calculation as a chain of true equalities. Remember, these are all equal. So it should be this thing is equal to 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 this thing. And that was the thing we were trying to show, that this was equal to this thing over here. Okay. So here are some tips. So there's a lot of flexibility there. What are some tips, some guides? Here's what I would recommend. For one, it's usually best to start with the more complicated expression. Uh, that's really just because you won't have to invent as many things to prove the identity. So pick the side that looks more complicated and start massaging it, and then work out the kinks until you get to the other side. Another thing, multiply by a clever one. We've seen that all sorts of times in this course. One of the most powerful techniques in math. It shows up a lot here as well. So multiply by a clever one. That's another good trick. Rewrite the trig expressions in terms of sine and cosine only. That can help out a lot. Four, write sums and differences of fractions as a single fraction. Basically, find a common denominator and push those fractions together. You can also try adding a clever zero. There's both of them, right? Clever one, clever zero. And also factoring. So factoring is another way that can help you massage things so that you can prove an identity. All right, let me do an example here. I'll do this one first, and then I'll ask you to do a couple in a moment here. But we want to prove this identity. We're going to prove that this expression is equal to this expression. And here's how we do it. So we've got to start by choosing a side to work with and then manipulate it until we arrive at the other side, okay? So we get to choose which side we start with. In this case, I'm going to choose the left side, and I'm going to start with this, and I'm going to massage it until I get this as a result, okay? That's the idea. And the technique I'm going to use in this case is multiplying by a clever one. So here we go. All right, here is the left side. I'm going to take that expression and I'm going to multiply it by 1. I'm going to multiply it, in this case, by 1 minus sine of theta over sine of theta. There's a reason for that, and it's because that's basically the conjugate of 1 plus sine of theta. And I'm going to leverage a difference of squares in this situation. So I'm going to do this times this. That has the structure of a difference of squares, so it's going to become 1 minus sine squared theta. In the denominator, hold on one second. Sorry about that. Okay. In the denominator, there's just a product, right? Cosine theta times 1 minus sine theta. And then what happens? Oh, yeah. This right here, this is a modification of the Pythagorean identity. So remember, cosine squared theta plus sine squared theta equals 1. So that means that cosine squared theta is equal to 1 minus sine squared theta, just like that. Okay? Oop, hold on 1 second. All right. Yes. Okay. So we get that right there. So 1 minus sine squared theta is equal to cosine squared theta, and that's how we're going from there to there. Now, because we have two factors of cosine theta up here and one factor down here, we can cancel one of them. And then we're left with cosine theta over 1 minus sine of theta. And that is exactly what we wanted to prove, right? We wanted to prove that this side was equal to this. And that is what this chain of true equalities shows. It shows that this is equal to that. And that was the goal. All right. Okay. Now, I had mentioned the Pythagorean identity. We've seen this before, and this is what it's called. I even called it that before. This is the Pythagorean identity, and we even just used it in the previous example. Aside from this one, there are a couple alternate Pythagorean identities, these ones. And I call these ones the tanning identities. I'll explain why in a minute. But they're these two. 1 plus tangent squared theta equals secant squared theta, and then 1 plus cotangent squared theta equals cosecant squared theta. All right. So in the literature, these are referred to as Pythagorean identities, and they're kind of lumped in with the standard Pythagorean identity. And that's really just because they follow immediately from the previous identity, the Pythagorean identity above. We will prove one of them in just a minute here, but colloquially, I refer to them as the tanning identities because of a mnemonic that a former student told me for remembering them. And it's just kind of stuck with me ever since after they told me that like many years ago. So here's how you can remember the first one. You can remember the first one as I tan in a second. I tan in a second. That's it. And then you can remember the second one as I cotan in a cosecond. So I like to call them the tanning identities just as a cute way of remembering what they are. So I tan in a second. Just a little bit of a heads up. This is one of the ones that you're going to want to memorize. And the Pythagorean identity you should memorize as well. But again, if you've got this one, then you've got this one as well. It's not too bad. Actually, wait a second. Is that one of the ones I have you memorize? I think it is. The tanning identities. Yeah, yeah, it is. It is. This is what's nice because if you can memorize one of them, then the other one is the same. It's just co instead of not co. Okay. All right, where was I? Oh yeah, right here. So let's prove at least the first one, and I'll show you why these are called alternate Pythagorean identities. So we're going to assume that this one is true to begin with. And then when cosine of theta is not equal to 0, we're going to divide both sides of this equation by cosine squared. And watch what happens here. So we're going to divide both sides here by cosine squared. And then we're just going to massage a little bit. So we're going to distribute this factor to both of those terms. We get this plus that. This is just 1 over cosine squared theta. Then this is just equal to 1. But notice here we have sine squared theta over cosine squared theta. That's tangent squared theta. So, and this is just secant of theta, secant squared theta by the definition of 1 over cosine, right? So there's the tanning identity, I tan in a second. Um, Dividing by sine squared of theta instead yields the second identity. So you can practice that one on your own if you want a good exercise. You can do that there. All right. Actually, here, maybe I'll just throw this up. Think about it for a minute. Maybe try that one on your own. Think about it. All right. Say something out loud, maybe even just repeat this, okay? And then try to work that out. Try to work it out on your own and see if you can derive the other tanning identity. All right. Okay. Next ones we're going to talk about are the even odd identities. We've seen these in practice a couple of times, but it's this whole collection right here. It's just stating the even or oddness of these functions. So here, sine is the sine of negative theta is negative sine theta, cosine negative theta is cosine theta, tangent negative theta is negative tangent theta, cosecant negative theta is negative cosecant theta, secant negative theta is equal to secant theta. Cotangent negative theta is equal to negative cotangent theta. So in summary, except for cosine and secant, all the other functions are odd. So these ones are even functions, and these ones are odd functions. Wait, sorry, my bad. I had that totally reversed. Forget I said that. Um, these functions are odd functions, and these two are even. And again, the reciprocal nature, so reciprocation doesn't change that even oddness. So if you know that sine is an odd function, its reciprocal is also an odd function. Same thing with cosine. If you know that it's an even function, its reciprocal is going to be an even function. That's one of the reasons I say this down here. I don't recommend that you memorize these formulas. It's really not worth memorizing it, and it's easy to forget if you try to memorize this table. Just think about the graphs of the functions and then think about what I just said about reciprocation. So if you can remember the graph of sine of theta, which you should, you can see that it's odd, right? It's an odd function, and that's it. If you remember the graph of cosine, you can see that it's even, right? It's symmetric about the y-axis. And then for tangent, the again, tangent is an odd function, and you can just see that by thinking about what its graph looks like. So that's how I would recommend memorizing these. We're going to prove one of these here, and then I'm going to leave the rest of them for you to do an activity. So here's the proof of that sine is an odd function. So for any angle theta, sine of theta is the vertical displacement from the x-axis of a point x comma y on the unit circle by definition, right? That's by definition. So we pick a point on the unit circle, and the vertical displacement of that point is sine of theta by definition. Yeah, just like this. Now, by the definition of a negative angle, and the definition of a sine function, we're going to get the result. So a negative angle goes clockwise, right? So if this is the angle theta, the angle negative theta is this one right here. And because this angle is negative theta, what's going to happen is this displacement is going to be equal to negative y, because this is equal to y. So down here we have negative y. So that means that sine of negative theta equals negative y. But what is y equal to? Y is equal to sine of theta. So sine of negative theta, which is equal to negative y, is equal to negative sine of theta, and that's what we were trying to prove, that sine of negative theta is equal to negative sine of theta. And that's pretty much it. That's pretty much it. The same figure in a similar argument reveals that cosine of negative theta is cosine theta. You can actually just use the same picture here, right? Same idea, right? If this is the angle theta and this is the angle negative theta, or I should say then this is the angle negative theta, here the x value is not changing. So it doesn't matter if this was positive or it was negative, the x value is unchanged. So in other words, cosine of negative theta equals cosine of theta. Pretty cool stuff, right? Okay, I'm going to leave the remaining ones for you to do an activity. It's going to be a similar argument. It's just really helpful to get comfortable. It'll help you get comfortable with that picture, the definition of sine and cosine and tangent, and so on. So I'll save those for later. All right. Now, let's talk about a whole bunch of identities. All right, here we go. We're going to start with the angle difference identity for cosine. Let me explain it, then we're going to prove it, and then we're going to prove a whole bunch more stuff after that. Um, so here it is. Let alpha and beta be real numbers. Then cosine of alpha minus beta is equal to cosine alpha times cosine beta plus sine alpha times sine of beta. All right. This is what's called the angle difference identity for cosine. And the utility of this particular formula is that if you wanted to know cosine of a difference, this lets you express that value in terms of cosine and sine of the original angles involved with that difference. So that's the utility here. It's like, if we see this, we can convert it to this. And if we see this, we can convert it to that. That's the utility there, all right? Now we're going to prove this identity using an algebro-geometric argument, and then all the other identities that we derive in this whole section are just going to follow from algebraic proofs. This is like the only geometric proof that we need. And it's a pretty cute proof, so I want to go through it. It seems technical, but it's really quite elegant. And I hope you enjoy it. So here we go. So for ease, we're going to assume that this relationship holds between alpha and beta, but it holds for any alpha and beta. We're just going to do this to show this case because it's the easiest case to prove. But this holds for any angles alpha and beta. They don't have to have this relationship. In particular, we're going to say alpha is less than beta. We're going to assume that they're positive and that they're less than 2 pi, just so we can set up a picture like this. Now, I'm going to zoom in on this. Give me a second. There we go. I'm going to zoom in on this, and we're going to set this up. So here is the angle alpha. Oh wait, do I have this backward? Hold on a second. I have these backward. My bad. These should be switched. Yeah, we're going to assume beta is less than alpha. There we go. Beta is less than alpha. I'll fix that on the slides afterward. But okay, so this is the angle alpha. This is the angle beta. And then when we take their difference, what we get is this angle in between right here. And I hope you can kind of see that, right? So here's alpha, here's beta, and when you take the difference, you get the difference, that space in between, right? Now, take a look at the points. So I've got the points labeled here. This point here, by a unit circle trigonometry, is the point cosine alpha sine alpha. And this point here is the point cosine beta sine beta by, again, unit circle trigonometry, right? I called this A1, I called this B1. Now what we're going to do is we're going to take this triangle and we're going to rotate it clockwise by beta radians. So we're basically going to tip this down so that this line falls on the x-axis, just like that. Okay, so we took that triangle and we tipped it down so that that side lays on the x-axis right like that, okay? All right. Now, there's a reason we did that, and that's actually because it's going to make things equivalent, but also easy to calculate. So here we go. Now that we've rotated things, this new point is 1 comma 0. So B1 is going to B2, which is now 1 comma 0. And now this point up here, by unit circle trigonometry, is cosine of alpha minus beta, comma sine alpha minus beta. There we go. All right, now let me zoom back out here. Okay, there we go. Now what we're going to do is this. So there's this long calculation. I heard all of you gasp just now. Oh my gosh. Yeah, don't worry, don't worry. This happens in math. It can happen a lot. It's okay. Take a deep breath. We're going to make sense of everything that you see here. Remember, don't let this overwhelm you. I know it's very easy to get this like twinge of anxiety. Trust me, I know that exact feeling. That's okay. Part of doing math is learning how to cope with that emotion. And one way I have found to cope with that emotion is to just go piece by piece. Remember, you're not expected to look at this page and be like, "Oh, I got that in like a second." No. That's not an expectation that any of us have, okay? So, let me explain what's going on here with this equation to start. When we rotated that triangle, the distance between the points that we had marked on that circle did not change. So back here, when we do this rotation, the distance here, this purple line, is the same as this purple line right here. That length has not changed. So in other words, the distance between A1 and B1 is equal to the distance between A2 and B2. There it is. So those two distances are equal. Now, remember the distance formula. The distance formula we've seen a bunch of times. We're going to apply it here, and we're going to apply it twice. Now, the coordinates of the points are a little bit messy, but that happens all the time. So don't worry about that. The coordinates can be really, really gross. Just follow your nose, go step by step, walk carefully, write your calculations as a chain of true equalities, and we'll make it. So here we go. This is the distance formula. This is the like x2 minus x1 plus, oh sorry, squared plus y2 minus y1 squared, x2 minus x1 squared plus y2 minus y1 squared, and you take the square root of those, right? Square root, just like so. And now we're going to square both sides. So we're going to square this side to get rid of those square roots. And now this is the messiest part. This is the messiest part. Multiply everything out and combine like terms. So this one actually takes up two whole lines. So when I multiply this out, I get this. Okay, maybe you can kind of see it. Cosine alpha minus beta squared minus 2 cosine alpha minus beta plus 1 squared. There it is. Over here, the minus 0, we kind of saw this before when we did this in a previous proof. Minus 0 is just going to disappear essentially, and we get sine squared of alpha minus beta. Now, this side's going to be a little bit messier, and this is the part that takes two lines. So when you FOIL this out and FOIL this out, you'll get this, and you'll get plus this. That's it. Okay. Now what are we going to do? Well, we're going to do a bunch of clever things. So check this out. I'm going to highlight this. Notice here we've got cosine squared alpha minus beta and sine squared alpha minus beta. So we've got cosine squared plus sine squared. Well, by the Pythagorean identity, that's equal to 1. So that's equal to 1. And we've already got this 1 right here, and 1 plus 1 equals 2. So these three things that I highlighted in blue simplify to 2. That's it. And then this other term just remains. That term is still there, no change there. Now, let's look at this other side because we're going to see something very similar happen. We've got oh yeah, cosine squared alpha, sine squared alpha, and then we've got cosine squared beta, sine squared beta. So those are going to add up to 2, right? Because this is going to be equal to 1. Oops, sorry, to 1, and this is going to be equal to 1, and 1 plus 1 is 2. So we get 2 right here, right there, from those two things. And then the rest, right? Then the remainder. So there's still a bunch of stuff hanging around. So there's this on the right side and there's this on the left side. But check this out. Let me erase some of this stuff so it's not so cluttered. Okay, we can do some cancellation. Watch this. So in this equation right here, there's a term of 2 on both sides. So we can cancel it. 2 and 2, those are gone. Then what remains is this, and this. But every one of those terms has a common factor of -2. Do you see that? -2, -2, -2. So we can cancel all those -2's. Cancel, cancel, cancel. And then what we're left with is cosine of alpha minus beta equals cosine of alpha times cosine beta plus sine alpha times sine beta. Boom. And that was what we were trying to prove. That was what we were trying to prove. That is the angle difference identity for cosine, just like that. Pretty cool stuff, right? Again, it all follows from this initial geometric argument, and then we bring it into the realm of algebra using the distance formula, just massage things a little bit, and everything works out really great at the end. Okay, now here's the fun thing. There's also an angle sum identity for cosine, and it's this. Let alpha and beta be real numbers, any real numbers. Cosine of alpha plus beta is cosine alpha times cosine beta minus sine of alpha times sine of beta. All right, let's prove it. And here's the good news. Proving it is actually not as technical as the proof we just saw. What we're going to do is we're going to use the angle difference identity, and we're going to rewrite this sum as the difference of a negative, and we're going to use the even odd identities for sine and cosine. The proof is like 2 lines. Here it is. All right, check out this clever result. Cosine of alpha plus beta is cosine of alpha minus negative beta, right? But we have a formula now for the difference, right? For cosine of alpha minus or angle minus angle, and that's what we just proved. So here is me using the identity we just proved for the angle difference. Here we're going to get cosine negative beta, Here we're going to get sine of negative beta. But remember, cosine is an even function. So cosine of negative beta is cosine beta. And sine is an odd function. So sine of negative beta is negative sine of beta. And voila, there it is. That one just fell right out. That one just fell right out. Okay. All right. Moving on. So now that we have an angle sum and difference identity for cosine, we will derive the sum and difference identities for sine by combining those results and the fact that sine and cosine are cofunctions. You might remember those things are cofunctions. They're basically just phase shifts of one another. So we can leverage what we already know and leverage the fact that they're cofunctions to easily get an angle sum and difference identity for sine. Here we go. So remember, cosine of pi over 2 minus theta is equal to sine of theta, and sine of pi over 2 minus theta is equal to cosine of theta. So we're going to use those in just a moment here. All right. First we need this. This is just going to make things a little bit easier. So there's a slight difference here. Cosine of theta minus pi over 2 equals sine of theta. I've just kind of changed the order of the difference here, but we're going to see that that doesn't matter. Um, Cosine of theta minus pi over 2 is the same as this. Here I factored out a factor of -1. So I factored out a -1 from theta, and I factored it out from pi over 2, and then I switched their order. All right. In fact, here, let me throw the thinker up for just a minute so you can kind of look at what's going on when I went from here to here. Ponder that for a minute. Okay. All right. Now, cosine is an even function. So that means that cosine of a negative angle is the same as cosine of the positive angle. So this negative essentially disappears. But because cosine and sine are cofunctions, this is equal to sine of theta. And we just showed that this is true. This is really just kind of like a little technical lemma that'll help us prove the angle sum and difference identities for sine, as we're going to do right now. So here are the angle sum and difference identities for sine. Sine of alpha plus beta is equal to sine of alpha times cosine of beta plus cosine of alpha times sine of beta. Sine of alpha minus beta is sine of alpha times cosine of beta minus cosine of alpha times sine of beta. All right? And we're going to prove those right now. So here we go. Starting with the angle sum identity, we're going to use that result that we're going to use I should say, the cofunction relationship right here. So sine of alpha plus beta is equal to cosine of pi over 2 minus alpha plus beta. That's the cofunction relationship. Here, I'm just going to reassociate. So I'm going to distribute negative, or this -1 to alpha and to beta, and then I'm going to reassociate the results. So we get this right here. All right? Okay, now, if you kind of squint your eyes a little bit, notice that what we've got here is cosine of an angle minus an angle. That's an angle difference. And we've got a formula for that. We've got a formula for cosine of an angle difference, and that's being applied right here. So it's this plus this. That's it. All right. But remember that sine and cosine are cofunctions, and we're going to apply that again here and here. So cosine, this thing right here, that's going to become sine of alpha. And sine of this thing here, that's going to become cosine of alpha. And then at the end, we've got the angle sum identity. All right. Now, let's do the angle difference identity. Here we go. So we're going to use the same kind of trick that we used just a minute ago. Here, sine of alpha minus beta is equal to sine of alpha plus negative beta. And now we have an angle sum. But we already proved the angle sum identity just a moment ago. So now we're going to apply it, and we get this as the result of that angle sum identity. Cosine of negative beta, well, cosine is an even function, so the negative doesn't matter. You get that. Sine is an odd function, so you're going to get negative sine of beta. And so this becomes that. There's that negative. And now we have a formula for the angle difference. All right. Whew. A lot of proofs, just boom, 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 falling right out, falling right out. Okay, so this is just kind of a summary of what those identities are. Here are the angle sum and difference identities, angle sum and difference identities. A couple of notes before we move on to an example involving these. I do not require you to memorize these in my class, okay? For other instructors that are teaching this, they may require you to memorize it, but I do not require you to memorize the angle, sum, and difference formulas for a couple of reasons. For one, the only utility you will really see for these in the calculus sequence is doing a couple of proofs. So, for example, you need these when you're going to prove like the derivative formula for sine and cosine. So you need them for a proof, but you don't really need them for a lot of the problems you're going to be working on. The other reason is, frankly, from what I've witnessed in my experience with teaching students, this type of thing is a nightmare for students with dyslexia. So I do not like to require students to memorize it because the formulas are very, very similar. They're just slightly tweaked one from the other, right? They're almost the same formula, except one piece has been moved around, and they're very, very easy to misremember. And rather than test your ability to remember dozens of formulas, I would rather you use these formulas for something meaningful. So you do not need to memorize these in my class, okay? Another note, you will see these things get used in your major courses, especially when you talk about combining waves. So physics majors, engineering majors, you will see these later on in your major courses, and maybe your professor will require you to memorize them then. Well, guess what? You can memorize them then. You don't need to memorize them now. All right. Okay. That's my little disclaimer about memorization there. Now I want to talk about an important cautionary note, because this is a common mistake that people will make. Note very, very well that the angle sum and difference formula is not just splitting the cosine over the sum or difference, right? Cosine of alpha plus beta is not equal to cosine alpha plus cosine beta. Check it out, right? Cosine alpha plus beta, it's not just splitting the cosine up between those two angles. That's not how it works. It doesn't work algebraically, it doesn't work geometrically, it doesn't even work intuitively, okay? More intuitively, what I'm saying here is like the horizontal or vertical displacement that occurs from traveling a bit more or less around the circle is not the same as just adding the individual horizontal or vertical displacements. Um, so beware. It's not just like distributing these things. Yeah, it doesn't work that way. Same thing with sine. Sine of alpha plus beta is not sine of alpha plus sine of beta. Okay, so beware of that error. That's a common error. All right. Now let's see the utility of this type of an identity. Let's see where we can use it. We're going to find an algebraic expression for cosine of 75 degrees. And I think you all might be able to do this one on your own to start. So I want you to think about this one for a minute. So think about it and now verbalize something. Maybe you could ask yourself, what does it mean to write it as an algebraic expression? Okay. Now try to work it out on your own, and I'll give you a couple of hints right now. Use one of those, well, I'll just say, use the angle sum identity for cosine, and remember that an algebraic expression doesn't involve trigonometric functions, okay? Those are my two hints. Try it now. All right, here we go. So the first thing to note here is that 75 degrees is not one of the standard angles, right? So it's not like we can immediately jump to the answer. However, one thing we can notice is that 75 degrees is equal to 30 degrees plus 45 degrees. That's kind of cool, because these two things are standard angles. And if we want to know cosine of their sum, well, we have a formula for that now, right? We have the angle sum identity. So we can rewrite cosine of 75 degrees as cosine of 30 degrees times cosine of 45 degrees minus sine of 30 degrees times sine of 45 degrees. And the beauty here is that these are all standard angles, and you've memorized the cosine and sine values for those standard angles. Cosine of 30 degrees, okay, what's the triangle look like? right? 30 degrees is the shallow one. So cosine's the long leg, root 3 over 2. 45 degrees, that's the diagonal. The legs of the triangle are the same length, root 2 over 2. Sine of 30, again, that's the shallow one. So sine is 1/2. And then sine of 45, that's the diagonal. They're the same. Root 2 over 2, root 2 over 2. Oops, there we go. Now, the only things that are present are algebraic expressions, and we're just going to simplify. Uh, Common denominator of 4, so we can pull out a 1/4. Square root 3 times square root 2 is square root of 6, and 1 times square root of 2 is square root of 2. So cosine of 75 degrees, this is having written it just in its plain form. Now we're expressing this value in an algebraic form, right? So this is an algebraic number, and here it is written in an algebraic form, just like so. Pretty cool stuff. Okay, now that you've kind of seen the trick, try to do this one, all right? So same kind of deal. Find an algebraic expression for sine of 5 pi over 12, all right? So think about it for a minute. Okay. Say something out loud, and then work it out on your own, and we will do it together in a moment. All right. Okay, so same kind of deal. What we're going to do is we need to try to re-express 5 pi over 12 in terms of a sum or difference of standard angles. So here's how we're going to do it. 5 pi over 12 is the same as 2 pi over 12 plus 3 pi over 12, which is equal to pi over 6 plus pi over 4. And that's the gold right there. This is a standard angle, this is a standard angle, and we have an angle sum formula for sine. So we can rewrite this as this, and now we only have to work with standard angles like so. All right? Okay, so what's pi over 6? Well, see, pi over 6 is the shallow one. Sine of pi over 6 is 1/2. Cosine is root 3 over 2. Pi over 4, the legs are the same length, so we get root 2 over 2, root 2 over 2. Factor out a common factor of 4, 1/4, I should say. And then we're left with square root 2 plus square root 6. So again, an algebraic representation of this is that. That's right. Okay. All right. Now we can do something that's even a little bit more complicated with these angle sum formulas here. So let's say we know this. Suppose we know sine of alpha is 4 over 5, and we know alpha has to be in the second quadrant there, right? This is that's Q2 between pi over 2 and pi. Suppose we also know that sine of beta is negative 2 root 5 over 5, and we know that beta has to be in the third quadrant. What is an algebraic expression for sine of alpha plus beta? All right. This one can be a little bit tricky, but if you want to try it on your own, go for it. So you can think about it for a minute, maybe chew on all the pieces for a moment. Verbalize something just to give your brain that feedback, get the juices flowing there. And then try to work it out. See if you can find an algebraic expression for sine of alpha plus beta. You're going to need to use the angle sum formula. So maybe you can start with that. Just look back at the previous pages, the previous slides, and you can just recall that formula that way. All right. Okay, let's do it together now. So if we want to use the angle sum formula, we're going to need to know the sine and cosine of the individual angles. Now we're given sine of alpha, but we're not given cosine of alpha. And we're given sine of beta, but we're not given cosine of beta. And if we want to use the angle sum identity for this, we're going to need those values. So what we're going to have to do is we're going to have to do a little bit of pre-work, you could say. We need to use this information to figure out what cosine of alpha is, and we need to use this information to figure out what cosine of beta is. So that's the first step. There we go. So we can use the Pythagorean identity again because cosine squared alpha plus sine squared alpha is equal to 1, right? So using that identity, we can rewrite it like so. In fact, let me just refresh your memories. of what that is, cosine squared alpha, oops, plus sine squared alpha equals 1. And we're just going to move things around. So we're basically going to shift things around so that we have, oops, cosine squared alpha equals 1 minus sine squared alpha. That's what we're doing right there. And that's how I'm getting this expression right there. Now, we would take the square root of both sides of this, but remember, every time you take a square root, what do you need to include? A plus minus. And this is one of those situations where it is critical to include that plus minus because we're going to have to pick either the positive or the negative result. And that depends on this additional information that we have about the angle itself. So keeping the plus minus the whole way, we can simplify it to that. So cosine of alpha could be either positive or negative 3/5. We don't know which yet. However, we are given that the angle alpha has to be in the second quadrant, right? So remember, second quadrant is over here. And when we're over here in this quadrant, cosine is a negative value. So this is a situation where we need to pick the negative value that results from that square root, from taking that square root. It's not going to be the positive, it's going to be the negative, and we find that cosine alpha is negative 3/5. All right, now we're about halfway there. So we have sine of alpha, we have cosine of alpha. Now we need to find cosine of beta, and the argument is going to be pretty much the same. We're just doing it again. So we need to figure out what cosine of beta is going to be. Again, using the Pythagorean identity, we're going to get that cosine of beta is equal to, sorry, cosine squared of beta is equal to 1 minus sine squared of beta. There we go. Right here. But we know what sine of beta is. Sine of beta is given to us. It's this right here. So when we square this, we're going to get this right here. Is that right? Let me double check here. So 4 square 5 over 5. Think that's right. Hang on one second. Let me double check that calculation. Yeah, that's right. That's right. Okay. Just checking my work because I was like, wait, does that seem right? Yeah, it is actually right. Because when you square this, you're going to get 4 times 5 over 25. 5 over 25 is 1/5, so you're going to get 4 over 5, just like so. Um, yeah, and then 1 minus 4/5 is 1/5, which I'm just rewriting like so. And again, we don't know if we need the positive or the negative outright. We need to use this additional information, what we know about the angle beta. And in this case, the angle beta is in quadrant 3, so it's down here somewhere, right? And if we're down here, once again, cosine is negative. So we need to take the negative result of the square root in this case, just like so. All right, now we have everything we need, and now we can put everything together. So we're just going to mush everything together using this angle sum identity. We know sine of alpha, we know cosine beta, we know cosine alpha, we know sine of beta, and then we're going to multiply everything, combine like terms, and we get 2 root 5 over 25. Oof. That's a long one, huh? That's a long one. Okay, let me do this. Okay, I've got one more example of using this. But let me say this. We still have quite a bit more to go. This is a bit of a longer lecture. There's a lot of content. So now would be a good time to kind of take a break. So if you want to take a break, just pause the video here, stretch your legs, go to the bathroom, get some sparkly water or something, and we'll start up again in just a minute. Coffee. All right, welcome back. So, hope you had a nice little break there. We're going to pick up where we left off, and we're going to do this example here, which is another use of the angle sum identity for sine in this case. um, Let me read the statement here, and then we'll talk a little bit about what to do. So here it says it wants us to write sine of cosine inverse of x plus sine inverse of y as an algebraic expression in terms of x and y. And then we're going to provide restrictions on all of these things. So I'll do this one just because it can get a little technical, and it's kind of similar to what we did in the previous example already. But the main thing I want to point out here is this. remember cosine inverse and sine inverse, those are angles, right? The arc trig functions, the inverse trig functions spit out angles. So these expressions here are angles. And what we're doing is we're doing sine of an angle sum. So because we're doing sine of an angle sum, we're going to use the angle sum identity for sine. We just need to find all of these individual values. So that's what we're going to do. This is what I just said, right? Already we know right away that x and y have to be between -1 and 1 because they're cosine and sine values. And cosine and sine values, the outputs are between -1 and 1. So right away we have those restrictions on x and y. All right? Now, in order to figure out what to do with these, we're going to give these angles names. So we're going to let alpha be cosine inverse of x, and in that way we get x equals cosine alpha. And we're going to let beta be sine inverse of y, so that y is equal to sine of beta. Now, because we are dealing with those inverse trig functions, we now have those restrictions on these. We can see those restrictions. Alpha has got to be between 0 and pi because it is that's the restricted domain for cosine in order to even talk about inverse cosine. And then beta's got to be between -pi/2 and pi/2, again, because that's a restricted domain for sine before we can even talk about inverse sine. All right. Now, considering those restricted domains, we know that sine of alpha has to be positive. Sine of alpha has to be positive, right? Because alpha is in this interval. It's up here. And the sine values up here are all positive. So sine of alpha has to be positive. And cosine of beta also has to be positive because beta is restricted to this side, right? It's on this restriction. And on this restriction, all the cosine values are positive. So this is another one of those situations where the restricted domains are important. The plus minus that occurs when you take a square root is important, and it's all coming together right here. Now, we can use the Pythagorean identity again to figure out that sine of alpha is equal to this. In this, yeah, remember the Pythagorean identity, cosine squared alpha plus sine squared alpha equals 1. And that's going to become 1 minus, oops, sorry, sine squared alpha equals 1 minus cosine squared alpha. And then you take the square root. And when you take the square root, normally you would get a plus minus. But because we know that sine of alpha is positive, we have to take the positive result. There we go. So we can rewrite sine of alpha as this, square root of 1 minus cosine squared alpha. And then remember, cosine of squared alpha, well, cosine of alpha is equal to x. So cosine squared alpha is equal to x squared. And that's what we get right there. Similar result for cosine beta, 1 minus sine squared beta, but y is equal to sine of beta. So sine squared of beta is y squared. Now we have everything we need. Whew. Oh, man. Need like a sweat rag here. It's a lot of work. We've got everything we need. We have cosine alpha, sine alpha, cosine beta, sine beta. Now we can use the angle sum formula. I'm going to plug it all in right here. This is alpha, this is beta. Now we can use our angle sum identity right there and just plug in what we calculated in the previous slides. Sine of alpha, cosine beta, cosine alpha, sine beta, right there. And now notice this result only contains algebraic expressions. There you go. All right. Now the angle sum and difference identities for tangent. Here we go. You ready? These ones we're going to derive in the activity. All right. So I'm not going to do those ones here. We're going to do those together when we meet to do the activity associated with this section. I guess maybe a little bit of a spoiler alert before I say this. So spoiler alert, you're just going to use the ones that you know for sine and cosine because remember, tangent is sine over cosine. So Spoiler alert, you're going to use those when we meet together to do these activities, all right? Okay, now enough of angle differences and angle sums. Let's talk about double angle identities. So here's the next kind of set of double angle identities, and we're going to use what we already know to derive these. So we can leverage the angle sum formulas for sine and cosine and tangent to derive the double angle identities. What these are these are formulas that are going to give us values for sine of 2 theta and cosine of 2 theta in terms of sine of theta and cosine theta, which is really handy. This is actually one of the ones you are going to have to memorize. So here we go. In this case, we're going to let the angles alpha and beta be the same angle. Just call it theta. So they're equal. Alpha is equal to beta, and we're going to call that common angle theta. Then the angle sum formula for sine ends up looking like this, right? Alpha and beta are both theta. And then this becomes sine theta, cosine theta, cosine theta, sine theta. But these are like terms. So we can combine them. We have two of them. So sine of 2 theta, because that's equal to 2 theta, is 2 sine of theta cosine theta. Easy peasy, right? That one's nice. That one's nice and easy. Okay, now let's do the same thing for cosine. Alpha and beta are now going to be equal. We're going to call them theta. So cosine theta plus theta is 2 theta. And this is the what the angle sum formula gives us. But that's cosine times cosine, which is cosine squared. And that's sine times sine, which is sine squared. And we're done. That's it. Cosine of 2 theta equals cosine squared theta minus sine squared theta. Just a bit of a heads up, this is another one of the formulas that you're going to have to memorize, all right? Just a warning there. Okay. Turns out there's actually a couple more double angle identities for cosine, and they follow immediately from this one, if I remember right. Am I right? Yeah, they follow immediately from this one. And well, this one and the Pythagorean identity. So these other ones are ones that are kind of good to have in your back pocket too. You don't have to memorize them, but they're good ones to recognize. So here we go. We're going to take what we know about cosine of 2 theta, and we're going to use the Pythagorean identity to re-express cosine squared as 1 minus sine squared. And the reason we're doing that is because now we have a common term of negative sine squared theta, which we can combine, and we get this different different expression for cosine of 2 theta, 1 minus 2 sine squared of theta. But again, it just falls very quickly from that to that. Now, rather than using the Pythagorean identity to replace cosine squared theta, we could have instead replaced sine squared theta, and then we get a different reformulation of this double angle identity right here. So there's two more just right there. Summarizing, this is what we have. These are the double angle identities for sine and cosine. This is the one for sine. You want to memorize that one. This is the one for cosine. You want to memorize that one. And these ones just kind of follow from that one right there. And the Pythagorean identity, which you should also memorize. All right. Let's use it. Let's use it to do something like this. Yeah, do something like this. So let's say we know that sine of theta equals 4/5, where the angle theta is in the second quadrant. Find numerical values for sine of 2 theta and cosine of 2 theta. All right. I do want you to try these ones on your own. They're not as bad as they might seem. So think about it for a minute, ponder it, mull it over. Right? Now verbalize something. Maybe, what do you know about cosine of theta given this information? All right, now try to work them out, and I will give you another tip. This is an important tip. Um, it's not just going to be 2 times this. All right, that's not what the formula says, right? Sine of 2 theta is not 2 times sine of theta. So you're not just doubling that number. You've got to use that identity. All right. Okay. Okay, now let's do it together, and we're going to piece all these things together and see what we get. So first, we need a value of cosine theta if we want to be able to use the double angle identities. Cosine theta appears in those identities. Now, we know that sine of theta is 4/5, And by right triangle trigonometry, we know that's going to be y over r. So that means that the radius of the circle involved here is 5. Now, here we're using, again, just the equation of a circle of radius 5, and we're going to have x squared plus 4 squared equals 5 squared. We can solve that for x to get x equals plus or minus 3. Now, again, we need to include the plus minus, and then depending on the context, choose which one we're going to need. In this case, again, we need the negative value because this angle here, this angle is in the second quadrant, so that means that cosine is negative. Oops, sorry. Cosine is negative over there. So we need negative 3. So cosine of theta is negative 3 over 5. And now we're golden. We know what sine of theta is. We know what cosine of theta is. Now we can compute the double angles. Here they are. Sine of 2 theta is 2 times sine theta cosine theta, which gives us that. Cosine of 2 theta is cosine squared minus sine squared, which gives us that. Not too bad. All right. Next set of identities. Here we go, moving along. The power reducing identities. So we can use those last two double angle identities for cosine. The ones where we had the 1 minus and like 1 minus 2 sine squared theta. We can use those to express sine squared and cosine squared in terms of single powers of cosine of 2 theta. That's actually going to be really handy in calculus 2, as you'll see. And we call these the power reducing identities because it reduces the power of the trigonometric function. Yeah, you're going to use these a lot in calculus, especially when performing integration. So the power reducing identities is another pair that you're going to have to memorize. And I believe that kind of exhausts the ones you're going to have to memorize. But I'll summarize it at the end. All right, so here we go. Remember that we had these two, I'm sorry. Wait, what am I doing? Sine squared. Oh yeah, we had this re-expression of the double angle identity for cosine, right? Just like this. Now what we're going to do is we're going to solve it for sine squared. Here we go. So sine, or here we go, just move this to this side, move cosine theta to the other side, and you get this. Now we're going to divide both sides by 2, and we get this. And this is the power reducing identity for sine. And what I want to point out here is this side has a power of 2, but this side does not. This side does not have a power of 2. And so that's one of the power reducing identities. Okay. Next, we're going to use that other formula that we got for the double angle of cosine, right? This one. And we're going to solve it for cosine squared. So we're going to, here, I'll actually just move this to that side and kind of switch things. And then we get this. Divide both sides by 2, and you get cosine squared theta equals 1/2 1 plus cosine of 2 theta, just like that. And again, notice the power has been reduced. So if we've got a power of 2 cosine, we're going to be left with a single power of cosine, but now it's cosine of 2 theta. That's the beauty there. Altogether, we have this, okay? Yes, altogether we have this. So these are the two power reducing identities for sine and cosine, and these are another two that you're going to have to memorize. All right, now to wrap things up, here is the list of trigonometric identities that you must memorize. You have to memorize them in my class, you have to memorize them in other people's class, you need to memorize them, period. So make sure you have these memorized. They are going to get used over and over and over and over again in calculus. So make sure you've committed them to memory. All right. I'll read them out and then I'll kind of explain why. Here's the first one, Pythagorean identity. You got to know that one for sure. This one, the tanning identity. You're going to be surprised at how often it pops up in calculus. The double angle formula for sine. Yeah, this one shows up a lot as well. It's really, really helpful in particular to be able to go from this to this. You'll see that a lot in calculus. Cosine of 2 theta. Again, if you have this, this can really, really help you solve things. And it's easy to get the other two versions just by kind of solving or using the Pythagorean identity in combination with that one, right? Then there's the power reducing identities, and these are honestly just critical when you're doing integration in calculus because this turns out to be very hard to integrate. But this is really easy to integrate. So it's kind of funny how that works, but you will see what I mean when you get into calculus. And then the last one there. So these six and slight modifications of these are ones that you should have memorized. So memorize these and then recognize the slight modifications, like moving sign over here or something like that, because that's how they'll show up. The other double angle identities for cosine can be helpful, and they follow from the power reducing identities. So there's that. The other tanning identity can be helpful, but again, if you know this one, I tan in a second, you get the second one for free. I cotan in a cosecond. That's it. Now, kind of going back to that disclaimer at the very beginning of this lesson, this is obviously not all the trigonometric identities, and there are many others that could be useful in different contexts, okay? This is not an exhaustive list. This is not an exhaustive coverage. An exhaustive coverage of all of these identities would take many weeks to do, okay? So this is just a core set of ones that will kind of carry you through calculus when you're doing those integration and differentiation problems, okay? Yeah, and I mentioned this about the angle sum and difference identities. You'll use those to prove things in Calc 1 and Calc 2 and so on. Um, there are also angle sum and difference, double angle, and power reducing identities for tangent that we did not state. And there are also half angle identities. There's just a million of identities. You can look them up on that Wikipedia link that I posted earlier in the lecture, but there's a ton, okay? We're actually going to prove several of the identities that are not here during the activity to help you practice proving identities, okay? So we're going to do that in activity to give you some practice. But these six are ones you absolutely need to be able to pull out of your pocket at any moment to use when you're in calculus, okay? Other ones you should be able to recognize a little bit and then look them up when you need to use them. All right. On that note, whew, let's play. Kind of hard to say that after all that work, right? The good news is, well, I'll get to work with you with these on these. Your other instructors will get to help you with these as well. You can take a breather. So this is why you should watch these lectures like the night before you come to class. Let it marinate in your brain while you sleep. All that kind of stuff. But this has gone on long enough, so I'll just say thank you all. And I believe there's only one more section left, or 1 to 3 more sections, I'll say. So thank you all again for watching, and I will see you next time. Have a good one, everybody.